So we talked about how we can have these 11 unique motifs here. So what do we see here? That we have a Z matrix, and we can look at all these potential starting points for the Z matrix here. And what this represents here is, this is the starting position. Here, let me explain what this is. So if we think of this as being starting positions 1, 2, 3, 4, 5, and 6, that's what these starting positions represent over here. Then what this is essentially is it's trying to track, okay, well, these are our starting positions. And here, this is sequence 1. Again, so the way that you see this is sequence 1, sequence 2, oh gosh, sequence 3, sequence 4. That's what this is saying. And what this Z matrix is doing is it's trying to map, to create this map here between them, where essentially what you're doing is we are going from here all the way to here. So we are saying, okay, that the probability of us starting in position 3 for sequence 1 is 1. And this maps here. So we're coming here. And then this part is mapping all the way to here. And lastly, this is mapping all the way to here. So this is sort of telling us, okay, well, these are the sequences. These are all the positions within. So the length is 6. And let's say that the motif really starts here at position 1. That's what this is saying. What this is saying that in the sequence 3, the motif is starting in position 4. So these are all the possibilities for the starting positions here. Oh, it's a little bit messy right now. So we have this initial Z matrix, and in the Z matrix, we're looking for the probability that the motif in sequence 1 starts at position 1. We're also looking for the probability that the motif in sequence 2 starts at position 2, and the probability that the motif in sequence 1 starts at position 3, and this is saying the probability that the motif in sequence 1 starts at position 1, at position 4. That's what this is measuring, and that's what this is saying over here, that this sort of lines up here where this is 1, and it's mapping here to the probability motif in sequence 1 starts at position 3. This is a 1. And what this 0 is saying the probability that the motif in sequence 1 starts at position 4 is a 0 here. And this is focused on the probability that the motif in sequence 1 starts at position 2, and the probability that the motif in sequence 1 starts at position 1. So that's what's being measured over here by this. So what we are looking at is we're seeing, okay, well, these are the possible motif positions, and this is where we believe that they start. And that's what we want in our Z matrix. So these need to sum up to 1, because the probabilities that if we look at a given sequence that the motif starts in each of those particular positions, that's why these need to add up to 1 here. This equals 1. These all need to equal to 1. So all along the Z matrix, the rows need to sum up to 1. And we also have the other sequence as well, but this needs to add up to 1. Need to sum to 1 here, and this also needs to sum to 1. So that's what we need over here. We need for these to all sum up to 1 for the sequence, because we can only have 4 possible starting positions along a sequence. And for those 4 starting positions, what they are is that the motif can only start in positions 1, 2, 3, or 4. So again, the CAG is corresponding to it starting in position 3 of sequence 1. That's what it means. There can only be 4 possibilities, because again, we can have CAG, we can also have GTC if we start in position 1. If we start here, or we can have like TCA if instead this is a 1, if we start here instead. Or we can have AGG which is this last one here, is if we instead start here. And this blue is where we currently are here. This is the current thing here. So that's what our Z matrix is telling us, and it's saying, okay, well, and this is where the motifs, this is where we believe that the motifs are starting for each of these 4 sequences. I mean, that's where we want to go, but in general, this is what the Z matrix is telling us, the probability that a motif sequence, so in sequence, like sequence 4, it's starting in a particular position. And we have 4 possible starting positions, so that's why this is going from 1 all the way up to M, which M equals 4 over here. So right now, we really don't know what our Z matrix is. It's equally likely that we could have any of those 4 starting positions, that are possible. So that's why we initialize this to being 0.25 for each of these values here. So we want to start off assuming that all positions are equally likely. So that's why we have this being like 0.25, 0.25, 0.25. And then what we do here is we next want to do the following. So we want to say, okay, M is equal to 4. So this value, each of these values here is essentially 1 over M, which is equal to 1 over 4, which equals 0.25. So that's what each of these entries ends. And again, the important thing is to note that along this whole sum along a row needs to be equal to 1. It all needs to be equal to 1. Okay, so that's what that needs to equal. And we assume that right now we really don't know where the motif starts. It could have been in that final output where we, that's like kind of like where we're trying to get to. And we're trying to find the probability weighted matrix associated with that. We really want this. We want to be so sure that this is the starting, and everything else is 0. But we don't know. GTC could be the motif, or TCA. We don't know. It could be any of these. Again, it could be like this, as I mentioned before. It could be like this. We don't know. So they're all equally likely at this moment. Or it could be like this CAG that we have right now. We don't know what it could be. So they're all equally likely. The row totals need to sum up to 1. So we also initialize a probability weighted matrix P using this following rule. So we said values matching letters in the subsequence. So subsequence is also a motif to some value pi. And we set other values to 1 minus pi over m minus 1, where m is the length of the alphabet. So here in DNA, the length is 4 different bases, because we can have A, G, T, or C. So that's why this will be equal to 1 minus pi, which is 0.3, because we usually tend to use pi of 0.7. And then m is 4, so that's 1 minus 0.7, 0.3 divided by 3, so it's going to be 0.1 for the other bases. So they look at this subsequence TAT that has a pi equals 0.7. So essentially we have a T in the first spot. So this is going to be 0.7 because it matches wherever there's a match, so matching letters is going to be pi. So this is a T. So in the first spot, this is spot 1. That's spot 2 here. And this last spot is spot 3 of the motif. So this is 0.7 here, and everything else is 0.1. Next is an A. So this A is 0.7 because, from here, this is where we get this 0.7 from. And the last one is a T, which is going to be our last 0.7 here. So that's where we get that from. So that's how we get it for the subsequence TAT. We get with pi equals 0.7. This is how we would get those values for this, for instance. So let me show you again, like how we would do this for the ones in our sequence. So again, our DNA alphabet has these 4 bases, A, C, G, and T. And we also assume that all bases have an equal background probability, which is 0.25. So since our motif has a width of W equals 3, then we need an initial probability weighted matrix with 4 columns, 1 for the background and 3 for the motif positions. And we have pi equals 0.7 for the DNA base and is 0.1 for non-DNA bases for each motif. as I mentioned before. So here, again, what is a background? What is a motif? So in this example here, what is the motif is, this is CAG. This here is our motif. This is our motif over here. And then these other parts here are really just the background. This is the background. This is non-motif, non-motif. This is the background here, AGT. ACG is his background, and C, T, and C, these are all the backgrounds, non-motif positions. So that's what those are. Let's see. So what we have here is, this is how we have our probability weighted matrix, where the backgrounds and non-motifs have zeros, zeros, and zeros, and zeros here. And along the motif, we have these three positions, positions 1, 2, and 3. And then we gather this information on, the starting position inside the motif. So this is the probability of having an A in position 1 of the motif. This is the probability of having a C in position 2 of the motif. And this is the probability of having a G in position 3 of the motif. So these are the different bases along the motif, the different positions. So, and these are the backgrounds. So they're all like just non-motif positions. And we assume that it's equally likely right now for the background to be any of these 4 bases. So that's why they're all 25% here. What we are using here is we're using this idea that pi is equal to 0.7. So that's why we're saying it's 0.7 if the motif starts with an A, 0.1 otherwise. And one of these is going to be true because it can either be an A, C, G, or a T. So this is 0.7, motif starts with an A, 0.7 if it starts with a C, 0.1 otherwise, 0.7 if motif starts with a G, and 0.7 if the motif starts with a T. So that's what this is saying. And similarly here, this is like 0.7 if the motif second base is an A, a 0.1 otherwise. And again, this is where this value comes in. And what we see along here for a probability weighted matrix is that the sum of all of these needs to be equal to 1. So this sums up to 1 here. This is sum up to 1. Similarly, these need to sum up to 1. That they need to add up to 1. That's what this rule is saying here. For instance, like these need to sum up to 1 as well. That's what this is saying here. All the probabilities need to sum up to 1. Along all the rows, because on each position you can either have an A, a C, a G, or a T. So they must add up to 1. So we're going to initialize all 11 of these probability weighted matrices, 1 for each of the motifs. So we had 11 unique motifs from the 4 sequences that we found. And I'm going to also walk through another example again, where again, we are really going to assume this, that that pi is equal to 70%. Wherever it's a match, it's 70%. Non-matches, it's not. This is a percent, 70%. So this is a G. So what happens is we're going to see, okay, we're going to go find where the G is over here. This is G. So it's 70% here. Then we're going to look for the T, and we're going to say, okay, the T is 70% over here. So that's also over here, this match. And lastly, for the C, we're going to find, okay, the C is here, so 70% here. Everything else is 10%. So that's how we figure it out. And again, the backgrounds are always going to be 25%. So we basically look along the motif, see where, okay, this is a G. We're going to make this first base here 70% here, which is what our pi is. Everything else 10%. Similarly here, this is a T in the second spot, so we make the 70%, everything else 10%. And this is a C here, so we're going to make it 70% and everything else 10%. That's the rule that we follow here. And we do this for all 11 of the probability weighted matrices, so I was showing an example here with GTC. So this is GTC again over here. And we can kind of see that for all of them, we have 25% for the background probability, 25% again, you can see it's all 25%, right? But what makes each one different, from the others is the location of the 70%, which is based on these different motifs here. So again, ECG, for instance, because the first spot is an A, that's why this is going to be 70% for the A here. This is the A. This spot here is a C. That's why this is a 70% for the C. And this is a G in this spot, which is why this is a 70% here for this. Similarly, apologies again, it's kind of a little bit messy, but like this is a G here. So this is a 70% here for this G. And this is a C here, so this is 70% here, 10% for everything else. And this is an A, so 70% here for having an A in the third spot of the motif because it itself is GCA. So again, these all add up to 100%, each adds up to 1, 1, 1. And so let's do another example just to make sure you understand this. And this is based on a pi equals 0.7. So again, like over here, GAG, we're going to get into GAG as well as another example where there's a G here. So that's why it's 70% here in this first position. The first position is a G. So if we see the G here, it's 70%.
For beginners, lesson 1. Today we're going to talk about variables.
Okay. So here's another example just to make sure that you understand. So for C, C, and A, what we're going to see is that, okay, well, the first two positions of the motif are C, so that's why these two are 70 and 70. And the last spot is an A, which is why this is a 70% here in that spot. So you see, again, basically, that this is they differ, like these initializations all differ, but they all have a background of 25%, but they just differ. So this is a CGG again, and then we looked at AGT again. So A has 70% the first spot, G has 70% for the second spot, and T has 70% for the third spot. So that's how we initialize these 11 different probability weighted matrices. And it's going to be helpful because that's sort of like one of the inputs that we use for this EM algorithm. That's going to give us all the other things that we need to figure out. Because in the end, what we really want to do is we want to get this. We want to find these motifs here. We want to find the probability weighted matrix and find the positions that we are starting in for each of these sequences. We want these to be ones and zeros. We don't want to get these 0.25s. We want to be definite about what is the starting position. So that we have these 11 ones, and this will be our best bet for how to start, for the motifs. So I'm going to kind of talk about our checklist of information that we've collected so far. So we have our 4 different DNA sequences. Each sequence is 6 bases long. And then we also have 3 bases in each motif. We have a pseudo count of 1, which is used for smoothing and estimating probabilities, which I'll talk about in the M step. We have 4 possible starting positions for the motifs and 11 unique motifs. So we talked about how we have 4 possible starting positions, because of the 4 possible starting positions, come here, from here. And we got this as well from like looking here about all the possible starting positions. And we'd figure those out like from this analysis here of how we start, we have 4 possible starting positions. Okay, that's what's to come, but let's kind of go back a little bit. So we are check our checklist of information. So like with SpongeBob, we've got all this information. So we have our different DNA sequences, 6 bases for each sequence, 3 bases in each motif, a pseudo count of 1, that's to help us not have any zero probabilities for any bases, 4 possible starting positions for the motif, 11 for the motifs, and 11 unique motifs that we've detected. We have an initial Z matrix of 0.25 value. So again, this is 1 over M. Each value is 1 over M here. So here, again, just don't confuse it with the backgrounds, because if whatever this value is, if we have more starting positions, this would change, because this is just frankly M 1 over M, where M is the number of starting positions for the motif. And this is 11 initial probability weighted matrices, 1 for each motif. And we use this idea okay, so for each of these, we're using this idea, like, okay, so this is one of the probability weighted matrices. We're using this idea that wherever we have a match, wherever there's a match, it's 70%. That's what our pi is. And it's 10% for non-matches. So we have these 11 different motifs, probability weighted matrices for these motifs. So later on, what I'm going to do is I'm going to be starting out our example. I'm going to be starting out the example with this. I'm going to start out with this here. Like this GAG is what I'll be focusing on. So this will sort of get all this attention, is this motif right here. I'm going to use this one and then sort of figure out what everything is in this algorithm. So we have 11 possible motifs, but I'm going to use GAG in our example, which is coming up. And that's what I mean when I say we use this initial motif GAG probability weighted matrix. That means that we initialize a probability weighted matrix to these values here to work with. And again, you can see that based on this matching rule, we do get some diversity in what these probability weighted matrices look like. So we have these 4 DNA sequences, and I just want you guys to see that we can look at them and calculate how many bases of each type there are. So for instance, if we look at T here, we have 3 of them, 3 T's in this data set, 3 T's. And since we have 4 sequences of 6 bases, that's where we get this 24 from. 4 times 6 is 24. So what this is our basic expectation maximization approach. So we're given a parameter W. W here is our width, which is equal to 3, because each of our motifs is length 3. And we're given a set of 4 sequences. So what happens here is that this is our initial step. We have 11 unique motifs. We have 11 unique motifs that we have. So each motif has its own PWM. We will try out each motif separately. And for each motif, we do the following. So we set initial values for P0. So the first example I'm going to do is going to involve this GAG. I'm going to use GAG right now. I'm going to use GAG, but we're ultimately going to do this for all of the 11 motifs. So I'm going to set our initial probability weighted matrix. And then using this probability weighted matrix, what I'm going to do is I'm then going to use the E step, which is called an expectation step. In our expectation step, I'm going to re-estimate my Z matrix using this probability weighted matrix for GAG. So what I'm going to do then is I'm going to take this and I'm going to use it in this E step to re-estimate this Z matrix. Get the updates. Instead of being 1 over M for each entry, I'm going to get some better results now. Then I'm going to take this re-estimated Z matrix, and then the end step, what I'm going to do is use this to then derive an updated P matrix. And what I'm going to do after that is I'm going to then calculate the log likelihood using my Z matrix and my P matrix. And I'm going to select the motif that gives the highest likelihood. It gives us and then please run EM to convergence. That's what we want to do. So I want to select the motif that gives us the highest log likelihood value using our updated Z matrix and our probability weighted matrix. And then I'm going to run EM to convergence. So expectation maximization. So we have 11 unique motifs. Each motif has its unique probability weighted matrix. We will try out each motif separately. And then for each of the motifs, so we're going to start out with GAG. What we're going to do is we're going to use the probability weighted matrix to then update our Z matrix in the E step, use this updated Z matrix in the E step, then in the M step, which is known as maximization, to then re-estimate our P matrix, and then use this information to then this information right here, use this then in our likelihood function to then, find that likelihood. And we're going to find the probability weighted matrix that gives us that highest log likelihood value. And we're going to use that. So that's sort of how this will work. So I'm going to kind of dive into it a little bit more right now. So in this E step again, what we're trying to do is we're trying to estimate the starting positions in matrix, in the Z matrix at step T. So here we're starting with T being 0, the first iteration. So this is 1, J plus W. So here the width is 3. So that's why this is 3 here. This length is equal to 6 here. That's what this is over here. And then what this part is this is the motif. And then these parts here are just like non-motif positions. So this is just background. This is also just background. So this J can be anything from, J can just be pretty much anything from 1 all the way up to M. And here M is 4. So J can really just be, if it's 1, then there's no background in the start, or it can be all the way to M, which is equal to 4 here. So this point here, this product is just like this pi sign is a product function here. So this is before motif, and then after motif. So that's what this corresponds to. This here is the motif part is pretty much just this part over here. This part here is a motif. The background of after the motif is just this part here. And then before the motif is just this part here. So that's sort of how to understand this part. So if we were to look in this example here, what we see again is for the background that like let's take this guy down, and then what do we see? That in this situation here, right here. So like what this is saying is that xi is the ith sequence. So this is our x1, this is our x2, x3, and this is our x4. These are the sequences here. And Zij is 1 if the motif starts at position J in sequence I. So that's what we're trying to figure out like right now. That's what we're looking at right now, is that following information. That this is before motif, motif, and then after the motif. And we're saying here that let's say that we're starting here at position 3 here. That's what this is saying. This is position 3. So this is 1, 2, this is 3, and this is like 4, for instance. But and this is 5, and this is 5, and then this is 6, right? So like what this is saying is that if we're starting in position 3 here, that's what this is saying. It's 1 if motif starts at this position J in sequence I, and CK is a character at position K in sequence I. So what this CK is, it can be A, C, G, or T. It could be one of those values right here. One of those. And we're seeing, okay, well, this is the motif here. This is the motif. Is this part here. And then after and before, these parts are the, this part here and this part here. These are all the background. So when we have this, and remember, we're just choosing a probability weighted matrix. It can be anything really. And this is saying that what's the probability of us observing a given sequence if our motif starts in a particular spot J in that sequence, and we have some probability weighted matrix. And this is the formula that we use. This is like before the motif, the background, and this is after the motif, the background as well. And this is the, so yeah, both of these are the backgrounds. And this part here is the motif. So we have 11 unique motifs, but for now, let's just focus on using GAG. Let us see what it looks like if we have GAG here. And we're going to do this for the other 10 motifs as well, but we're going to use the probability weighted matrix associated with GAG here. So where we have a G, we're going to have 70% here, and this first spot. And then for this A, we're going to have a 70% in the second spot here. That's what this is saying. And then for this G in the third base, that's why this is a 70%. And everything else is 10%. And the backgrounds are all 25%. And all these rows sum to 1. So let's just focus on sequence 1, for example. Okay, so we're focused on sequence 1. So we have a width is 3 because the motif is 3 bases long. Our length is 6 since each sequence is 6 bases long. And I is 1 here because we're looking at DNA sequence 1. We are honing in on this sequence. This is the sequence we're focused on. We're focused on the sequence. The sequence 1 right now. Okay. So now within this sequence, we are going to then change this a bit and say, okay, now what's the probability of X1 and X1 in particular being equal to G, T, C, A, G, G? What is the probability we observe all those bases there? If we have a particular starting position for our motif and the probability weighted matrix, which here I'm saying that we're using motif GAG. That means that the probability weighted matrix that we just happen to initialize everything with corresponds to that for this motif GAG. And again, there are 11 possibilities for our initializations, 11 motifs. We could have chosen any, right? And we will. We're going to choose all of them and then choose the one that gives us the highest likelihood and work with that and proceed with that, right? But in this case, we're choosing GAG right now. And we're focusing on this first sequence. And we have all this information here. And what's the probability we observe all these bases in this first sequence? If we're using that probability weighted matrix for GAG, and we're using this sequence here, we're trying to find this sequence given this information. And we have 4 possible starting positions along this sequence. So that's what this is equal to. So in this example here, we see that here in this example, let's kind of just bring it into focus a bit more. So again, for the starting positions, we could have starting positions 1, 2, 3, or 4. So we're focusing on right now on sequence 1, which is what this is here. And we have so many possible starting positions. There are 4 different starting positions. Again, how do we know that? Because we could have had this as our starting GTC, or we could have like PCA be another position, or we could have AGG be another position here. So many. But let's just say, so that's what this is, J equals 1. Correspond. So this is this one is this 4. This one right here that we're looking at is corresponding to position 3. This other one here, this purple one, is position 2. And this green one right here is position 1. Like all of these. So right now what we're focusing on is we're just going to focus right now on the position 3. That's what we're focusing on. So we're just looking at the motif starting in position 3. So what's the probability again that we're going to observe this entire sequence if a motif starts in position 3, so if it's CAG, and we have the probability weighted matrix for GAG. So we just plug in like J equals 3. I'm going to be plugging in J equals 3 in this formula here. So I plug it in, and you can see what these are here, right? So what do these zeros mean again? These zeros refer to these background probabilities. And what this part here is this is the K, this is like the position in the motif. That's what this is saying. This is the position in motif. That's what that is. That's what this is K minus 3 plus 1 here is. And why is that the case again? Just a reminder that when we're looking in our probability weighted matrix, this is a reminder again, is in a probability weighted matrix. For the backgrounds, they always have the 0 here, 0, 0, 0 here. And within the motif parts, we always have the second index here is telling us the position in the motif. So this is like position 1, probability that we have an A in position 1 of the motif. Position 2 of the motif, position 3 of the motif, and that's what these K is, like the positions within the motif. So that's what that is telling us here. So these are like the particular bases that we observe, and CK can be A, G, T, or C. So it can be A, C, T, or G. That's what these characters can be here. Any of these. So now when we plug it in, what we see is that this is K equals 1 to 2. So the first 2 bases are going to be like background probabilities. Then these next 3, so this would be K equals 3, 4, and 5. This is 3, 4, and 5 will be like in the motif. And then this part, again, the last one will be the base. So just to kind of mention it again here, let's just see what exactly again this is referring to. When once I multiply it out, I get this formula here. So this part here corresponds to these here. These are all the motif. And then these parts here, these backgrounds, this is the background part, non-motif. It corresponds to these here. And then this one again corresponds, this last lonely guy here corresponds to CK, the 6th character. And so you can see that this is the motif part again. So in essence, what this is saying is if we use the initial probability weighted matrix for the motif GAG, that's initialization, what is the probability of us observing sequence 1, given that the motif for sequence 1 starts at position 3, so it corresponds to CAG, instead of at positions 1, 2, or 4. So we could have had any of these other positions. So we started out here with our Z matrix. We started out with essentially saying that all of these positions are equally likely. We didn't know where the motif starts. And now we're just focusing right now on sequence 1. So what, like, we're just trying to say, okay, well, let's say that we really want to come here. We want to have bunch of zeros and ones. We want to be sure where that motif starts. So what we had initialized it is instead to 0.25s. We want to instead say, okay, well, like, so we're just focusing, so we can just ignore right now, just for right now, we can just ignore, let's just ignore this part here. Let's just focus on sequence 1. So let's chop off the other parts. They're not important. Let's just have these all become zeros. All become zeros, have this become 0, have this become 0. And then this part here is actually going to just become 1. What is, if this is the case, if this is 1, what are the chances of us even observing that sequence 1? What is the chance of we getting all those bases? That's what we're trying to focus on. Like, what happens if that's the case? So in this situation here, what we're doing is we're saying, okay, again, we're just focusing on sequence 1. So we'll have these others just be ignored for now. And you'll see that row 1 is the first sequence here. And column 3 is the starting position of 3. And if we set this equal to 1 and everything else as 0, what would happen? What would be the probability? That's what this is saying. If we set this equal to 1, we're using the probability weighted matrix for GAG. That's what this is saying. Then what is the probability we would observe this sequence, of like A, G, C? I think it's like what is the probability that we would observe that sequence? Let me check again what that sequence is of GTC, AGG. And we have so many possible starts, but let's just keep everything else as 0 and see what would happen. And we're going to just focus on the sequence 1 for now. So again, in sequence 1, we are just focusing on CAG, G using GAG's, probability weighted matrix. So these are all the characters, the 6 characters, and these are all 6 bases for sequence 1. And what we see here is that this C corresponds CAG. This part here is just these 3 parts right here. And these 2 are the background, and this is the motif here. This part is the motif, the C, A, and G. So along the motif, this is position 1 of the motif, the C. This is position 2 of the motif, and this is position 3 of the motif, this G. And we can just sort of map them in a way where we see that C3, 1, this is C3, and that's why this is here. A C4 of 2 is just this A over here. And C5 of 3 is just this G here in the 3rd location. That is how we get C3 is C, C4 is A, and C5 is G. So C3 is C. You see this mapping, C3 is C, C4 is A, and C5 is G. That's how we do this. And these are all, this G0 is just what this is saying. The C6, this G is what this part here is. The C6 is 0. These are all this background, not really like not motif parts. That's what this part here is. these parts here, I kind of focused on these parts here. The C1 is this G, the C2 is this T, and that's what we see here. C1 is G, C2 is T. Then we see here, we're going to take the initial probability weighted matrix, and we see PC1 is 10%, PA2 is 70%, and PG3 is 70%. Because we're looking for C, A, and then G, because that is the motif that happens if we look in sequence 1 and we start at position 3, that's the motif, and then that's what we're going to look for in the current probability weighted matrix. We're going to say, okay, what are those values? So then we're going to just take these values and plug the respective ones in. So what this is it's saying here that this 10% is this 70% comes in here, and this G part is here. So this is the CAG. We have that motif here, C, A, and G. That's where we get this from, the C in position 1, the A in position 2, and the G in position 3, using this motif. And you see that these are both 70 and 70% because it's very similar to this motif, except, we have a C instead of a G here. So we plug it in and we get this value here. And what this value is saying is that we have a 0.000766 probability % chance using the probability weighted matrix that was initialized for the motif GAG. If we start at position 3 in sequence 1 for the motif, of the motif and sequence 1 starts at position 3, the probability that we will observe the sequence 1, that we will get all these bases like G, T, C, A, G, G, the probability that we would get such a sequence will just be 0.000766. We focused on this branch here, so of this tree. So the probability of us getting sequence 1, that's a cute little monkey, of us getting sequence 1, given that the motif for sequence 1 starts at position 3, is 0.766. So we're thinking of the probability of us observing essentially a G in this, a G, then a T, then a C in position 1 of the motif, an A in the position 2 of the motif, a G in position 3 of the motif, and then just another G. That's what we found. And it's really small. It's like 0.766%, right? So we just focused on this, but we have the other positions we can focus on. So we just focused on this one branch. We just focused on this one branch right here. We focused on just this blue branch right here. But we need to also focus on the other possibilities. Like what would happen like if we started at position 1 and we look at GTC? Or what would happen is if we started at position 2 instead and have TCA? Or what would happen if we started at the last position and have AGG? What would the probabilities be of us observing that sequence? So since we had just zoomed in on one specific starting position of CAG, we just looked at this one branch. So we need to look at the tree for sequence 1. So we had only looked here. This is what this blue part was telling us, is we just had focused on this. That's what this 0.765625 is. If we start in this position, so this is J equals 1, 2, 3, and 4. And we had looked previously at like what happens is if we start with, the CAG here, 10, 70, 70%, right? The CAG. And now we're looking at the other things too. Now, like, let's say that we start instead at sequence, the motif for sequence 1 starts in position 1. Well, that gives us a 0.000109375 chance. And we can do it. What if we start at sequence starts for 1, it starts at position 2? What would that look like? And then we can try that out as well. So that's what we see here, that we can go along and we can just sort of vary it and see, okay, here this is GTA, that's what this is saying. This is saying, okay, this is TCA. Okay, what's the probability? So if we start in position 2, what's the probability of us observing sequence 1 if the motif instead is TCA here, it's starting at position 2? What's that probability then? So it's going to be like 0.0000. It's really small. So I don't think it's really high there. But again, this is all using this GAG motif values because we plug them into this formula here based on those values. We take these other J values here, like J equals 1, 2, 3, 4, and we go back to this formula here that I showed you, where I mentioned that J can be 1, 2, 3, or 4. We just use J equals 3 here. We can go back and change J, have J be 1, have J be 2, have J be 4, and see what are the probabilities. You know, if we have, if let's say we start in position 2, you know, what's probability of x1 given x1 comma 2 equals 1, and that probability weighted matrix. It might seem odd, why are we doing this for GAG in particular? That's just one of the initializations for the probability weight matrix. We have like 11 total. So yeah, we just finished doing this all for one sequence, looking at all 4 possible starting positions and then seeing, okay, well, how likely is this sequence, you know, if the motif starts in each of those different starting positions? That's what this is telling us. So what you'll see here is that we have, this is the example that we worked out together with this 0.766, you know, probability of, you know, of the sequence 1 if the motif starts at position 3. So we found these other values, and the way that it works is here, this point right here maps right here, and this value like right here maps here, and like this value here maps here, and like this value here, again, just alternating colors just to make it a little bit easier, maps right here. We just take these values and we put them into our matrix. And remember, you can just kind of ignore this part right now. You can just ignore this part. We're going to get to that next. But what you see is that, okay, well, this actually sums up to 0.001, which we're not too happy about because this should actually sum up to 1. These are probabilities, you know, so we're not happy about this. We want them to sum up to 1 because the probabilities of us starting the motif in positions 1, 2, 3, or 4, they all need to add up to 1. So to get this to add up to 1, for instance, what we will do is we will take this, for example, let's take this 0.000109, and instead we are going to do this. We're going to have 0.000109, and we're going to divide this by 0.00100. So we're going to divide it by the total. That's not normalizing it. And we're going to do the same thing for this too. So we'll just take like this value now, and we're going to just divide it by, so we're going to take 0.0076563, and then we're going to divide it again by 0.001. And that way it will add up to 1 instead, and we'll be happy. So please normalize Z so that each row adds to 1, because the sum of each row in the Z matrix should be 1. The Z matrix represents starting position probabilities for the motif. So we identified this error. So now what we do is when we divided it by that total before, so again, we divided each entry here by 0.001, then it sums up to 1, and we are happy. That's great. We're happy. Because it equals 1. So what I had mentioned before in this example is that we sort of had started out in this example by focusing in sequence 1, the probability of getting sequence 1 if the motif started in position 3 for this probability weighted matrix. So we were just looking at one branch. Then I'm like, wait, we can have other starting positions for this first sequence. Let's try all 4 of them out as well. So we tried all 4 of them. What if it starts here, position 1, What if it starts here in position 2, in position 3, in position 4? What is the probability of us getting those sequences? And we got that. We focused on this part, but we had excluded this part over here, So we focused on the tree as well. So we had forgotten this part, but we focused on the tree for that same. We focused on the tree for all possible m values here. So we zoomed out from just the branch with the monkey on it to the whole tree for that sequence. The sequence is a tree here, but we want to also focus on all of the sequences. So we want to see the whole forest. We want to see everything, not just the monkey on the branch in one tree. We want to see everything, the whole forest. So let's focus on sequences 2 to 4 and also update the Z matrix. So this kind of shows you how we update the Z matrix for one sequence. Let's do it for the others. The same idea. Again, sorry, this should be actually say the probability. This part should actually read what this title says. So this is the probability of sequence to given motif starting position. And we just vary it, from 1 all the way to 4. We're varying it. And that's what this is saying. J equals 1 means we're starting in position 1 and we're going 2 and 3. And what we see here is that let's kind of stamp it a bit about which ones we would really love given the highest probability. So it seems here that the highest one would be for j equals 3 because it's the highest. Here, as of now, it also seems that the highest is for j equals 4 because it's the highest probability of the sequence, highest probability of x3 given j equals 4. So what this is saying is, again, this is saying probability of x4 equals ACGG AG, given that the motif starts in position 4 and we're using PWM for GAG. That's what this last one is saying. That's what this is calculating for us. The one that we love here, that's what this is calculating. The probability of getting the sequence A, C, G, G, A, G, if the motif starts in this 4th position and we're using the probability weighted matrix that's initialized for GAG. So that's the highest one there. And we're going to tend to focus on the ones that have the highest values. And here again, what we find is in this stamp that it seems like that this one is the highest. So the starting in the 2nd position here. So now we have the same thing. So we fixed sequence 1, but we're kind of unhappy right now with the other sequences because they don't add up to 1 right now. The rows don't add up to 1. So we're not happy right now. So we just need to normalize everything so that they add up to 1. Sorry, my star looks kind of bad right now. But we just need to normalize everything. So again, like for instance, we have to take the 0.005359 and divide it by 0.0055. And then we normalize it so that the rows sum to 1. And then we're happy again because everything sums up to 1. So we have the probabilities that of each starting position. So right now we're going to keep our Z matrix as is, like this, but because it sums to 1. But in the end, when we will converge at the end, what we really want is to find the one in each sequence, the position that gives us the highest likelihood of the highest probability of observing the sequence. So here we have a 0.765625 here, which is seeming like the highest value. What this is 0.9744232. These are all very small numbers. this one here is the highest, and this one here is the second highest. So what we're going to do is we're just going to slash everything else out to zeros. This slashed out, this slashed out, this slashed, and slashed. And we're just going to give these values all ones. And so we just make these all ones. Because in the end, the one that's the highest probability, when we converge, though, we're going to make that starting positions 1 and everything else 0. Oh, sorry, I also forgot this too. We also want this to be 0. And these all will be 1s here. But that's when we converge. We're just going to assign that to 1s and 0s respectively. So in our M step, we re-estimate this P matrix using the updated Z matrix value. So we kind of got from 1 over 4 of 0.25, we have a better estimate for our Z matrix now after the E step, the expectation step. So now in the M step, we're going to re-estimate our P matrix using the updated Z matrix values. So we currently have this P matrix, and again for the GAG motif, but because we're looking here, we have this P matrix right now. Let me actually move this here. This is our probability weighted matrix that we used. Because, you know, G 70%, then A 70%, and G is also 70% again. So we want to now say that we kind of updated our Z matrix. So now we also want to update our P matrix as well. That's sort of how this expectation maximization worked. That we had started out with the Z matrix of all 0.25s, and we remember we were trying to change it around a bit. Now we also want to update our P matrix using this new Z matrix. So we will use this M step here. A PC, comma K represents the probability of characters C, which again can be A, C, G, or T in position K. So values for K equals 0 represent the background. And the pseudo counts, this we know is 1. And this is also 1 here. And we use a pseudo count as Laplace smoothing because we don't really want to have like a 0 probability for any base. We just want to bump it up even a little bit, like that it has some probability that we will observe this character, this base in a particular location. So we kind of had talked about a little bit about like the total counts. That's what this NC is. This is the total number of C's in the data set. What K greater than 0 represents is this is the motif. And this is the background, non-motif. So what you'll find here is that this NC comma K, this is the total number of C's in the data set, so like total number of a given base in the data set. And the thing you'll have to do is you're going to have to first calculate what these values are for the motif. So you first need to calculate them for the motif. Then you can plug in those values here to find the probabilities for the background, right? So to find these probabilities for the background, we're going to need to find like NC comma 0. That's what this thing is saying here. So actually, let me explain it in a better way. So what this thing at the bottom is this is N C, sorry about that, NC comma 0. And what these values are is these values come after we found the motif values in each of the positions along the motif. That's what we are looking for here. So we first need to find these values for the motif for K greater than 0. Then we can use those to find these counts for the background. So I'm going to explain it a lot more right now. So don't worry if you don't see this right now. So here T represents the iteration. And again, we are looking at the probability weighted matrix at a given iteration, which is this here is our first iteration. And we use pseudo count equals 1 for smoothing and estimating probabilities in the M step. And because this is a 1 for all bases, then this is a 1 here. And then this is a 1. And because we have these 4 bases, we can just pull this out. This 1 comes out here. And that's where we get this 4 from, because we are having these 4 bases. And that's sort of how we derive that. What this is saying here, let me get down to here. And now I'm going to say that what this value is this is just the number of bases you observe in a particular spot along, which should just be the number of sequences, which is 4. So what this all is this is just 4 here, because this is the number of sequences, which is 4. The 5 sequences, and this would have been a 5, for example. So that's why we take this here, and then we get this. So the probability of observing a particular character in a specific spot along the sequence is just given by this here. We need to find the number of a given character in each position of the sequence, like whether it's background or it's positions 1, 2, or 3 of the motif. So you want to understand, why is it necessary that we have this NCK again? Well, it's involved in this probability. This NCK part is used here. And it's also used here in the numerator. So it's really helpful. Oh gosh. For us to determine this NC and K. And moreover, it's used over here. So he's kind of confused, right? What does it mean? So again, we want to first calculate what this value is for all the motif positions for k greater than 0. Then we can use those to calculate NC comma k equals 0. That's the background, the non-motif positions. So, well, what does this mean? Well, let me give you an example. So this is the sequence here, right? So we're going to look at all 4 sequences 1 to 4. And we're going to look here at the Z matrix. And let's say that we want to calculate NC comma K, with this C here is going to be base G. So we're going to focus at base G, right? So what this is saying is the number of G's in position 3 of the motif. This is saying the number of G's in position 2 of the motif. That's what this G and 2 means. That's what this is saying here. This is saying, okay, the number of G's in position 3 of the motif. That's what this 3 is. And this is this base here. That's how you read this again. And we want to just see how many G's do we have in position 3 of a motif. That's what we're trying to find right now. We're trying to find NG comma 3. So again, that's number of G's in position 3 of the motif, number of this base G in position 3 of the motif. That's what we want. So that's going to be really helpful, because in a probability weighted matrix, explain again what these are all like probabilities, and this is K, right? And we're looking for all the motifs where our G will be in position 3. That's what this is telling us. And because we have 3 motifs, that's what this is going, we have 3 motifs as a width equal to 3. That's why we have, that's why we're looking at these 3 positions here. 1, 2, and 3. So we're going to get all of the motifs that are possible for each sequence. Please look at the motifs that have a G in the 3rd position. Find the probability of us having this motif for the sequence, and that is given by our Z matrix. So Z matrix tells us the probability of us having a starting point in a particular spot in the sequence. So let's start with sequence 1. So we're just kind of scanning through and looking, does that sequence have a G in the 3rd spot? That's what we're trying to see. Okay, to begin with, okay, G, T, C, C, no, there's nothing. T, C, A, no, there's nothing. CAG. Oh yeah, that guy has a G in the third spot. That's how it works. So we go through all possible motifs of width equals 3 bases for sequence 1. Like so, since m equals 4, there are 4 possible starting points. Starting point 1, 2, 3, and 4. So what we see here is that, hey, okay, so this one has a G in the third spot. This other one also has a G in the third spot here, the G in the third spot. So if we start at starting point of j equals 3, we get a G in the third spot. And if we start at j equals 4, we also have a G in the third spot. So when we looked for starting positions, again, where G is in the third position of the motif, we found that j equals 3 and j equals 4 gave us those answers. So we have a G in the third positions of motifs CAG and AGG. That gave it to us. These correspond to start position 3 and 4. So we look for sequence I equals 1, start equals j equals 3, and sequence I equals 1, start j equals 4. We look at those. And that's what this is. I equals 1 is this one here, and j equals 3. So this is saying sequence 1, position 3. So we look for all the spots that match up for us. We pretty much just look here and say, okay, we found that the motifs, like CAG and AGG, for the first sequence that correspond to starting points 3 and 4, they had a G in the third spot. And that was our goal. Our goal is to find NG, 3, the number of G's in position 3 of a motif. That's our goal. It's so important to us. So we found that if we start at positions 3 and 4, those are having motifs, motifs of CAG from this third spot and AGG from this fourth spot. So what we're going to do is we're going to take these two values and include these. So this is what we want. That's what this formula here is saying, that we look at a given sequence. So here we're looking at sequence 1, and we're going to find where the motif in that position is equal to that character of interest. So we looked in the first sequence, we found all the starting positions, if there are any, that have that lead to motifs that have a G in the third base of the motif. And that was starting positions 3 and 4. Then we go into our Z matrix and we get those Z values. That's what we have to find. We need to find those Z values for those matches. That's why we take the Z at the position 3 and the position 4. So we also need to do this for sequences 2, 3, and 4 because we just scanned sequence 1 right now. We just focused on sequence 1 right now. We started here with sequence 1. Now we need to scan through the other 3 sequences. So we look for all the motifs with base G in the third position. And again, like what we do here is we just scan through. And I was seeing, okay, well, if I have a certain starting position, if I start out, so we finished the first sequence. So now let's look at sequence 2. If I start out with in 1, then I get GAG. Here, that's what this first one is saying. If I have the starting position of 2, I get my AGA, which is what this is here. Starting position of 3, then GAG. Oh, that's a match. Yay. This is also a match here, right? And then if I also start with starting position 4, I get AGT. Nah, it didn't work. So that's how we're keeping track. We're basically just scanning through all the possible starting positions. And I'll do this last one as well on this last row again. So we have CCA. That means that this is what it corresponds to starting in position 1. This is position 1, 2, 3, and 4 for the J. And if we start off with like this position 4, here we would get like this GCT, which is not a which is not what we were looking for. So we just kind of scanned through all the possible starts, found the motifs that are associated with them, and I've highlighted the ones that give us what we are looking for. This is great, has a G in the third spot, 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 G in the third spot. That's what we are wanting. And this is in a similar construction to our Z matrix, because a Z matrix is basically the probability of us having our motif starting and any of these four starting positions for each sequence. So again, I just sort of like blacked out the ones that are not important. So we're just focusing on these. And yeah, these are the respective Z values. You know, we wanted, these are the respective Z values. We wanted this one was a match. This one, this, 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 this. So we're taking all the Z values that correspond to our motifs. So essentially what we're finding is, what is the probability of us even getting motifs that have a G in the third base? Well, we just add up the probabilities for each sequence that we would have that leads us to having a G in the third spot. These are all motifs that are possible that have a G in the third base. And the probability of these motifs taking place corresponds to their respective values in the Z matrix. So we found these 8 entries with motifs that had a G in the third spot. So it's like a weighted average, where we want to find the expected number of times we can expect a G to have, to be found in the third spot of the motif. That's again what this 3 is saying. So we take this, we multiply each entry by 1, because that would be one instance of having a G in the third spot of the motif. This would, with a 0.7656% chance that we would have a G in the third place in the motif. If we have the starting here, or a 0.109% chance of a G in the third base, but it's based on the starting position here. That's what this is telling us. We just take all those values and we just sum them up. That's what the formula was saying, and that's what gives us 3.6949. So now we have this value here. We know that the formula that we derived above, and it's going to be based on your sequences. So you have to be careful, right? So based on this formula here, right here, what I got from here is actually this formula right here. So I'm going to just plug this in. I'm going to just plug this in over here. And I'm going to plug in 3.6949, add 1, divided by 8, and I'm going to get 0.5872. So there's approximately a 58.72% probability of us finding a G in the third position of a motif in this data set. That's what this is saying. A 58.72% probability that we find a G in the third position of a motif in this data set. So kind of what happened is I'm going to then put this 58.72% here in the probability weighted matrix. And I mean, I have to also adjust everything else, but I'm kind of showing you where it belongs. So then I'm also going to do the same thing for the others. So right now I was focused on, okay, well, what is expected number of counts, of 3.6949? What is expected number of G's in a third spot in the motif? Let me calculate that for the others positions in the motif. Let me calculate it out and find, like, this would be the number of expected number of C's in the second position of the motif, number of T's in the second position of the motif that we expect, number of G's in the first position of the motif. So when I do the same process like how I did it for G, where I kind of go through, like if I wanted to find NT comma 2, I would find all the motifs. I would look here at all the motifs that have a T in the second position. And I would so if I wanted to find out, like, again, just sort of like reiterating the same idea again, that like if I wanted to find, how did we find NT comma 2? Then the same idea here would be like, I'll just get rid of this, but I'll just kind of look for where I find a T in the second spot. Okay, this is a match right here. I scan again and I'm going to say, oh, okay, well, this is also another match. So you can just kind of scan through the whole thing. or you can go sequence by sequence, but you'll find, okay, well, there are these two matches, and let me look in the Z matrix. Let me find out the ones that are matching up for it. Let me sort of like take the Z matrix. Oh, X. Let me copy it here. Let me bring this thing down, for instance, and like, let me take this and let me deselect this part here. And let me just take this one as a match here. And this is another match. So I'm going to add these two values up. So 0.109375 plus 0.12069. I'm going to add those together. And that's going to give me, similarly to how what we got before, that's going to give me this n t comma 2 count. And then when I take that value, I'm going to just add 1 to it and divide it by 8. And then that's how I will get nt comma 2. So that's how we get that value. So then what happens is once we have this matrix here, so we figured this thing out, right? Expected number of counts. So we've come down to this level here. Then we can find the background counts for a given base by using this formula that was also there, which is nc comma 0 equals nc minus this over here. The width is 3, the motif length is 3 here. So we plug in 3 over here. So what we found before is that, like I'd shown how we found that the 3 T's and 10 G's and 5 C's and 6 A's in the set of sequences. So if we expand this out, this is NC minus, NC1, NC2, NC3. So we pretty much, the way that we find out the expected number of bases that we will find in the background is by taking the expected number of that base that we find in position 1, position 2, and position 3, or position 3 of a motif. So basically any time that base is found in a motif. That's what this is telling us, that the number of times, expected number of times we would find that base in a motif. And we're going to subtract that from the number of times we found this base in the whole data set. So if it's not in a motif, this is what it's saying. This is the times it is in a motif in either the first, second, or third base, because here it's 3 bases. If we had a motif of length 7, it would be the first, second, third, fourth, fifth, sixth, or seventh. So if it's in any of these bases in the motif, then we subtract it from the number of bases we find in our overall data set for that base, number of times we find that base, subtracted the number of times that base is found in a motif, and that tells us the number of times we can expect this base to not be found in a motif. That's what this is saying. So here, NG1, NG2, NG3, when we find these values, this is sort of telling us that we expected number of counts, and we would expect to find a G in position 1, maybe 2.18. So again, these are like averages, right? A G in position 2.167, that's the average times, and then a G in position 3 with 3.6949, which is what we had worked on deriving. So we take these up, and this tells us the expected number of times we're going to find a G in the motif in some capacity, whether it's base 1, 2, or 3. So we take those values and we sum them up. And we had found that there were 10 G's in this data set, but out of this, we found that, that like 6.051585 is the expected counts of G in any motif position, position 1, position 2, or position 3. So when we take 10 minus this value, we get 3.948. So what this is telling us is that we would expect to see around 3.948 Gs that are not in any motif positions. These are in non-motif positions or the background. That's what the 0 is, again, the background. That's what it's saying, like, that's the number of times you would expect to see a G in a background. So again, this is all based on what we found for our motif counts. That's why I was saying we have to first find our motif counts and then use those to find our background counts. And similarly, we can do these for the other 3 bases here. So we find the total number of that base that there is in the data set, and then we subtract from it the number of times we have expected to find that base in positions 1, 2, or 3 of the motif. And this really depends on the width. This goes up to W. So if we have 7 elements in our motif, this would go from NA3 plus NA4 plus NA5 plus NA6 plus NA7. It really depends. But here, this is for a width of 3. And so we would get these counts here. So we would expect an A in the background like 2.24, a C in the background 3.07, a T in the background 2.7356. So that's where we get these values from. And then I just put the background counts in here. And this is the same from before. So this is what we, now we have the background numbers and the probability weighted matrix motif values for the motif. And before, for GAG, we started off with this matrix, and then we then update it by using these counts that we derived. These are the expected number of each DNA base in a motif position. So we're going to use these values, and we're going to use this formula. So if we want to find the probability, of having, let's say we want to find the probability of having a C, or not C, C might be confusing, maybe a T in position 2 of this matrix, and we're here at iteration 0. That's why this is a 0, because we're like pretty much either on 0 the first, maybe we would just call it 1 just to be, safe. So this is the first iteration because we're just doing a first pass through. So this will be equal to, we're going to focus on this value here, and we're going to bring this value down here and say that, hey, it's equal to this, which is approximately 0.02300. Let's just keep like that, plus 1. And then we're going to have it divided by 8. So that's what it equals. We're going to just do this for this example, for instance, probability of finding a T in base 2 of the motif. So we take the counts, and then we add this number to smooth it with this 1 on the top, and that's how we get that value. So when we do that, we are busy getting all these values. That's how we derive all these values. These are just all those probabilities that correspond using this formula. So as I was showing for NT2, we just take it in here, we plug it in this formula here. And then when we get that, we just take that and we map this here to this. That's how we get those probabilities. So summary so far. So we had started out, sorry, this should be 11. So we had started out with an initial probability weighted matrix P for using this motif G, one of 11 possible unique motifs for this data set. And when we had this GAG, we had this probability weighted matrix, that we updated. So so we started out, this should be 70%, sorry. Then we had this Z matrix here with all these 0.25 values. So this is 1 over M. In our expectation step, we went from these values here all the way to these values here using our P matrix for GAG. And it would be different if we use another P matrix instead. When we have 11 options, that's why we try for each of these motifs. Then when we had this updated Z matrix that we got from our expectation step, we looked in our M step and we got our updated Z matrix and used that to get this updated P matrix. So the E step helps us update our Z matrix using our probability weighted matrix. Then in the M step, we use this updated Z matrix to get our updated P matrix. And that's what those computations were that we had seen. And what we get in the end are the following: a new probability weighted matrix and a new Z matrix. then what we're going to do is we're going to sort of calculate these probability values, like the probability of getting each sequence given each probable starting position and the newest probability weight matrix for GAG. So we're going to then run through everything again, where we're going to combine our Z matrix that we have updated and our P matrix that we've also updated. This is our updated, and this is also updated as well. We have updated this. We updated our Z matrix in the E step. We updated our probability weighted matrix in the M step. So using these updated values, we're going to calculate the probability of the sequence using this starting point of 1. We do this for every single possible starting position here. That's what we're doing. So in our log likelihood, so we start off with a total log likelihood of 0. Then for each of the 4 sequences, we're going through each of the starting positions possible. And we're finding the probability of having the sequence giving the starting position of the motif. So for the log likelihood, what we see here is that we have these 4 sequences. And like this is the formula. So we're going to go through each of the sequences and go through each of the starting positions and compute this value over here. So for this GAG, we're using this updated probability weighted matrix and our updated Z matrix. And we're calculating again the probability of observing each of these sequences using all possible starting positions. Then we're doing this for all 4 sequences. Then we're dividing this by 1 over M, where M is 4. And we get this value of negative 29.006. Well, what is this exactly again? Well, how we calculate the total log likelihood. So we were looking at the probability weighted matrix corresponding to the motif for GAG. And then this is the first iteration results. So, this is the sequence 1, sequence 2, sequence 3, sequence 4. So let's go into each sequence. So in sequence 1, we have these 4 possible starts, 1, 2, 3, and 4. And these are the probabilities of the sequence given the motif starting position. So, using the updated ones. So you see that this is slightly different. So this is like 0.002464990. This is now the probability of having sequence 1 if we are starting in position 3. This value is kind of a little bit different from what we found before. So let me just copy this for comparison. Before, when we were running this in our, when we were looking in our E step to find our Z matrix, I was saying, okay, well, let us find the probability of getting that each of those sequences. So let's scroll up a little bit back to the E step just for a bit of comparison again with what happened. Again, this is our M step here, but let's go back to our Z step a bit. In our Z step, what we had found is the probability of us getting sequence 1, given that the motif for sequence 1 starts at position 3 is 0.766. But now what we're getting is this value, which corresponds to 0.246490. So that this value has changed now. The probability of us getting sequence 1, given that the motif for sequence 1 starts at position 3, is now 0.246490%. That's a change. That's sort of showing you how changing the Z matrix and the P matrices, how that's sort of changing the probabilities of us getting each of the sequences. So that's what's happening in this likelihood. So again, we had gotten an updated Z matrices and we ran through each of these values, and these same values here are kind of what I've plugged in over here again. So we notice that a probability of us getting each of the sequences given the starting position, this is our J, and then we have our I, this is I equals sequence 1. And these are the probabilities here of the sequence. And then you just add up these probabilities for each of these sequences. So I'm adding up the probabilities here, and then I'm getting 0.002939. M is 4, so I take this total value and I divide it by 4 here. So I get 0.000184. And then I take the log, natural log of this value. So the natural log of 0.00184 is this. So again, what this is this thing divided by 4. So this is 0.0029339 divided by 4 is this. Then you take this value and you apply the natural log to it. So this is the ln of that value, which is 0.00184. And then what we get is this, is equal to this, negative 7.2161. That's what that is. Then we can also see for like sequence 2 here, that's sort of like sequence 2 is, let me just sort of like black it up a little bit here. This is sequence 2. It's right here. We take these values, we add them up here, we get our total. So these parts here, when we sum them up together, we get this value here. Then we divide by 4. Then we take the natural log of that value, ln of this, ln function of that gives us this, negative 6.9044. So what we see here again for x3, we do the same thing. We take the totals, we divide it by 4, and then we take the natural log and we get this value here. And then we do the same thing here again. So we take these totals here, we sum them up, then we divide by m, which is 4. Then we take the ln value of it, the natural log of that. And then we get this negative 7.62976. And then we just do one thing, which is just have to add these up together. So zooming out a little bit. We take these values here. Oh gosh. We take these values, and when we add them together, we get negative 29.0062. That's what we're taking there, and that's how we're getting those values. So the total log likelihood, if we begin with the P matrix for the motif GAG, is negative 29.006. That's what we did. So we were just taking these values using our updated probability weighted matrix for the GAG motif and our updated Z matrix, and then we recomputed these likelihood values using them. And this is the formula that you can use. Basically, in short, this is the formula that you can use for a given number of sequences. So we did this for this GAG, right? But I mentioned that we have 11 possible initializations that we can use for the probability weighted matrix. So we focused on GAG, but let's focus on these other 11 as well. So we had selected GAG and used that probability weighted matrix, but let's try out the other 10 different motifs, use their respective P matrices. Remember all those initializations with pi equals 0.7, and we can compute their log likelihoods. So then when we run this whole process, after running for one iteration, we need some direction, right? Like we just chose this one start randomly, right? We should choose all of these 11 possible starts and choose the one that gives us the highest log likelihood. And the one that is CAG. It's negative 28.817. So again, like the way that we'd run GAC, the way that we ran it, we got our values for it. for this for GAG, we had run it, and the values we got were this negative 29.00062. It's not the best. We want to find the one with the highest likelihood. So that ends up being CAG. So we'd run the same pipeline, everything that we've done for GAG, we run it again for the other motifs, and we get all their likelihoods, and we choose GAG because it has the highest log likelihood. So we select the motif that gives us the highest log likelihood, and that is GAG. So we will continue with GAG and run the EM algorithm for the Z matrix and the P matrix corresponding to CAG. So what we get is we start out off again with all 0.25 initialization 1 over m for all of these values for the Z matrix. When we finished, like how we were looking at the Z matrix for GAG, when we look at CAG after the first iteration, instead, these are the values that we get for the Z matrix. And then we started off with CAG, and it's instead of GAG, the CAG one. So I'm showing you again, kind of when we did this, we kind of traced through in detail GAG, but CAG gives us the best. But I'm kind of showing you a little bit about what happened behind the scenes for CAG. So behind the scenes for CAG, what happens is that, this is a C, this is a 70%, 70% here and 70%. And then we had gotten the updated Z matrix, sort of using this probability weighted matrix. And then when we use this updated Z matrix, so we first had our Z matrix set to being all like 1 over m values, like all those 0.25 values. Then we looked at this initial probability weighted matrix we had for CAG. In our E step, we updated our Z matrix so that it would look like this instead. And then we use this updated Z matrix to then re-update our P matrix in the M step here, and we get these values. And because this gives us the highest likelihood, we're just going to keep going with CAG. We're going to take these values here and run it to convergence. So what you see here is after one iteration, we went from here to here to here after one iteration. And this had given us that likelihood that was the highest likelihood. This Z matrix had given us that highest likelihood. Z matrix and this P matrix here, when we combine them, they gave us the highest likelihood of negative 28.817. I know it's a bit of a tie, but I'm almost not tie, but it's very close, but we still go with the majority one. That's like the best direction for us to go in, and then optimize that. So after one iteration, it looks like this. Then we just focus on this, and we focus on this Z matrix, and then we don't have to check any other motif. We move in this direction, and we keep running EM, like expectation maximization, iteratively, until the difference in the likelihood between the previous iteration and the current iteration is less than something. So the likelihood is no longer improving anymore. We've kind of like as much, we're stabilized. So after running this many rounds, our probability weighted matrix is converges here to this final value. And that's what